Alright, in this tutorial we're going to take a look at a selection of problems from the Special Right Triangles problem set that are part of the Google form linked in the description below. If you have not already seen my video on Special Right Triangles, I highly encourage you to pause and check that out first. I've linked that video in the description as well. Question number 1 asks us to solve for the missing leg x and hypotenuse y of a right triangle. We are shown one of the acute angles, 45 degrees. Since the sum of all angles in a triangle must be 180 degrees, the other acute angle must also be 45 degrees. That makes this an isosceles triangle. Since there are two congruent angles, the sides opposite those congruent angles will be congruent as well. That means that x is also 13. All that remains is to solve for the hypotenuse. We have a couple of ways of doing this. We could use the Pythagorean theorem, which is a squared plus b squared equals c squared. In this case, that would be 13 squared plus 13 squared equals y squared. We could also use the patterns that relate the sides of an isosceles right triangle. The hypotenuse is always the side length times the square root of 2. That means that y equals 13 times the square root of 2. Let's look at another one. This time, we are given the hypotenuse of an isosceles right triangle, and we are asked to solve for the legs x and y. Once again, we're shown that we have a 45-degree angle, and we know that this must be an isosceles right triangle. Since we have two congruent 45-degree angles, the legs opposite those two angles will be congruent as well. That means that x equals y. We also know from our isosceles right triangle patterns that the hypotenuse is always equal to the side length times the square root of 2. That means the side length for this triangle must be 7. Since it's isosceles, both x and y are 7. If you don't know or remember these patterns, remember you can always use the Pythagorean theorem. In this case, since the legs are congruent, x equals y, we'll have x squared plus x squared equals 7 square roots of 2, all squared. X squared and x squared makes 2x squared equals 49 times 2, or 98. Divide both sides of the equation by 2, and we have x squared equals 49. And x will be positive or negative 7. Since we're talking about the base of a triangle, we'll take the positive solution here. Question 7 from the problem set talks about a baseball infield with a right angle formed between each of the bases. If we go from home plate straight up to second base, we're drawing a diagonal through the square, bisecting the 90-degree angles into two 45-degree angles. In other words, we form two 45, 45, 90 isosceles right triangles. To find the distance between home plate and second base, we have to find the hypotenuse of that triangle. Well, recall that the hypotenuse of an isosceles triangle is equal to the side length times the square root of 2. Since the bases are 90 feet apart, the distance from home plate to second base will be 90 times the square root of 2. Of course, we could use the Pythagorean theorem here as shown in the previous problem. However, as you can tell, knowing those patterns really saves time here. In problem 8, we're asked about a 30, 60, 90 degree right triangle. Side length x is across from the smaller 30-degree angle, which means that it is the smaller of the two legs. Side length y is across from the larger of the two acute angles, the 60-degree angle, meaning it is the longer of the two sides. The hypotenuse of a 30, 60, 90 right triangle is always twice the shorter side. That means that 18 equals 2x, and x itself must be 9. The longer leg of a 30, 60, 90 triangle, which is y in this figure, is always the shorter leg times the square root of 3. That will be 9 times the square root of 3 for this triangle. Question 10 shows another 30, 60, 90 degree triangle, and this time we are given the longer of the two legs, 10 times the square root of 3. We know this because the longer leg is across from the larger of the acute angles, the 60-degree angle. The shorter leg, x, is across from the 30-degree angle. The longer leg in a 30, 60, 90 degree triangle is equal to the shorter leg times the square root of 3. That means the shorter leg, x, must be 10. The hypotenuse, y, is twice the shorter side, so in this triangle, y will be 10 times 2, which is 20. Looking at number 15, we have two triangles. We have an isosceles right triangle on the right-hand side, and we have a 30, 60, 90 degree right triangle on the left-hand side. We'll use those patterns to solve for the missing sides quickly. On the right-hand side, x can be found by looking at the hypotenuse of the isosceles right triangle. The hypotenuse of a 45, 45, 90 right triangle is equal to the side length times the square root of 2. That means that x must be 12. That also means that the height of the overall figure is 12, since this right half of the figure is an isosceles right triangle. Looking over to the left, we have the shorter leg 12 across from the 30-degree angle. The base z is the longer leg of the 30, 60, 90 triangle, which means it's going to be 12 times the square root of 3. Finally, we have the hypotenuse y of the 30, 60, 90 triangle on the left-hand side of the figure. It's going to be twice the shorter leg, so that would be 12 times 2, which is 24. Last one. Number 17 shows a right trapezoid. We can draw an altitude, shown here in red, and label the height by using the left-hand side of the figure. We created a 30, 60, 90 right triangle on the right, where this height in red is the longer leg across from the 60-degree angle. The longer leg is always the shorter leg times the square root of 3. So this segment in blue, which is the shorter leg, must be 10. That means that the other portion must be 14. And 14 is itself the value of y. To find the hypotenuse x, we'll just find 2 times the shorter leg. That will be 10 times 2, or 20.